Hello friends, welcome back to online lecture series on design of machine elements. So we have started this chapter in our previous lectures and we will continue. So we will do a quick revision of what we have gone through. So we started with introduction, that what is pressure vessel and where it is used. Then we discussed about the classification of pressure vessels, and it is done based on the dimensions, that is if the thickness is less than 1/10 of diameter, then it is thin shell, and otherwise it is a thick shell. And then based on the end construction, it is classified as open end and closed end. Then we discuss the two different types of stresses which are generated in the thin cylindrical shell due to an internal pressure. First is circumferential or hoop stress, which occurs in the longitudinal direction, and second is longitudinal stress, which happens on the transverse direction. We derived the equations for circumferential stress or hoop stress as well as longitudinal stress. So now we will move forward with our next and new topic, that is thin spherical shells which are subjected to internal pressure. So here now it is no more cylinder, it is a complete sphere. So here we have considered T as the thickness of this shell and P is internal pressure. Consider a thin cylindrical shell just wait. Consider a thin spherical shell subjected to an internal pressure as shown in the figure. Let V be the storage capacity of the shell, P as the intensity of internal pressure, D as the diameter of the shell, T as the thickness of the shell, and sigma T as the permissible tensile stress for the shell material. Now, in designing the thin spherical shells, we have to determine first as the diameter of the shell and second is the thickness of the shell. So we will evaluate these two dimensions. First will be the diameter and second will be the thickness. So let's derive it. On our whiteboard. So here first we will calculate the diameter of the shell. So as we know, the volume of any shell is given by V is equal to 4 by 3 pi r cube, where r being the radius of the spherical shell. Now as we know that r is equal to d divided by 2, that is radius is half of the diameter, so we will use that relation to make this in the form of diameter. 4 by 3 pi d by 2 cube. So here we will get pi d cube divided by 6. So this is the volume. So to obtain the diameter, we can convert this equation as d is equal to 6v divided by pi raised to 1/3. So this is the diameter that we have obtained. Now we will focus on the thickness of the shell. So due to this internal pressure, here this shell will rupture or fail from the center of the sphere. So we will write down first the equation. Force tending to rupture sphere which is given by P F is equal to pressure into area. So P into area will be pi by 4 d square. Now the resisting force is equal to sigma t into projected area or resisting area. So it will be pi into d into t. So which area is this? Let me show you over here. We are talking about this entire area. Okay, so this will be pi into d into t. Okay, so now we can compare these two equations. This will be equation 1 and this will be equation 2. So here p into pi by 4 d square is equal to sigma t into pi into d into t. So there are few things that will get cancelled. Sigma t. So here the evaluation of t will be pd upon 4 sigma t. So let's copy this portion over here. So this is the first thing that we derived, and here the second portion is this. So I hope that this theory is clear to all of you, and the same equations are also written here as final equation. So now we will move forward to our next theory, which is thick cylindrical shells subjected to an internal pressure. Okay, now we are here in which the thickness of the shell will be more than 1/10 of the diameter of the shell. So this will come into the category of thick cylindrical shells, and now we will see that what happens when such kind of thick cylindrical shells are subjected to an internal pressure. So here when a cylindrical shell of a pressure vessel or a hydraulic cylinder like or gun barrel is subjected to a very high internal fluid pressure, then the walls of the cylinder must be made extremely heavy or thick. So as you can see, these are the examples of the pressure vessels in which there will be extremely high internal fluid pressure, where we need to make the thickness higher. So this will come into the category of thick cylindrical shells. So if you recall, in our previous lecture I told you that in case of thin cylindrical shells, we assume the tensile stress as uniformly distributed over the sections of the wall. So let me give you this reminder that what we did over there as an assumption here. If you see, this portion, I am talking about this assumption that the tensile stresses are uniformly distributed over the sections of the wall. So I told you this, that this is applicable to the thin cylindrical shells. Okay. However, currently here in this case, but in case of this in case of this thick wall cylinder, the stress over the section of wall cannot be assumed to be uniformly distributed. So now this stress will be varying, that is its value will get changed in the radial direction. So they develop both tangential and radial stresses with values which are dependent upon the radius of the element under consideration. So now this theory will get bit complex mathematically. So here this is our thick cylindrical shell in which we have this inner radius Ri, if you can see, and we have outer radius Ro. So this is the entire thickness. As you can see that the thickness is more here. So now what we will do, and obviously P is the internal pressure. So what we will do, that we have done this kind of things many times in our physics as well as in some engineering topics as also, that we are considering an infinitesimal circular strip having a thickness of dx which is at the distance of x from the center. So this is the distance x and this is the thickness dx. Now as you can see, there are two kinds of stress distributions are shown in this figure. First is tangential stress distribution and second is radial stress distribution. As you can see here once again that the tangential stress is maximum at the inner portion, that is over here. This is maximum at the inner portion and it is minimum at the outer radius. And as far as radial stress is concerned, it is maximum again at the inner radius and 0 at the outer radius. So we will derive the formulas for both tangential stress distribution and radial stress distribution. So let RO be the outer radius as we have discussed in our previous slide, Ri as the inner radius, T as the thickness, P is the intensity of internal pressure, mu as the Poisson's ratio, sigma T as tangential stress, sigma R as radial stress, and first of all we will see the Lamb's equation. So here we will be assuming that the longitudinal fibers of cylindrical shell are equally strained. So here Lamb has shown that the tangential stress at any radius x is given by this formula. So this formula, we will not go through the derivation of this formula because in the reference book also it is given directly, so we don't have a derivation for this. We will simply accept this formula and continue our further derivation. Okay, so this is the tangential stress and the radial stress. See, what you will do, you will pause this video over here and note down this equation in your notebook. Okay, so the only difference between these two equations here is the sign. In the previous equation it was plus sign in between, and here it is minus sign. There is one correction that I need to do in the slide is here so here it is sigma R, so there I need to make a correction. That's it. So now we will continue with these two equations on our whiteboard. So this will be a bit longer derivation, so I hope that all of you will keep patience while I derive this equation. Let me first copy this Lamb's equation over here. So we will be using these two equations for the tangential stress and the radial stress. Okay, so let's begin now. Now as if you recall, in this figure we are only focusing on the internal pressure, because obviously this thick cylindrical shells contains a fluid which is at very high pressure, so they are more prominently subjected to internal pressure and not the external pressure, because on the external side we have atmospheric pressure. So it's better that we only focus on the internal pressure and we consider external pressure as 0 in comparison with the internal pressure. So here we will take Pi is equal to P. Let me me increase the thickness, and just wait for a while. So as I told you earlier that we will consider PO as 0. So internal pressure is P and external pressure is taken as 0. So now what we will do is we will modify these two equations parallelly. So here sigma T is equal to P R I square divided by R O square minus R I square plus R I square R O square Pi, because PO is already 0, so divided by x square RO square minus RI square. So now we can take the common terms outside. So P, just wait, here it is only P now. So P RI square divided by RO square minus RI square into the bracket 1 plus RO square upon x square. Okay, so this is sigma T. I hope all of you are getting this. And now we will do the same thing for the radial stress. Sigma R is equal to Pi Ri square divided by RO square minus RI square minus RI square RO square divided by x square into RO square minus RI square. So now sigma R is equal to P RI square divided by RO square minus RI square into 1 minus RO square divided by x square. So these are the two equations. Now as you see here, we discussed that the tangential stress will be maximum at the inner radius and minimum at the outer radius. So we will now calculate the maximum and minimum values of the tangential stress. So now sigma T is equal to sigma T maximum when we have x is equal to Ri, that is at the inner radius this will be the maximum stress. So now we can calculate sigma T maximum is equal to P Ri square divided by Ro square minus Ri square into 1 plus Ro square upon Ri square. So we have simply replaced x with Ri. Now if we further simplify this, then we will get P Ri square upon Ri square into Ro square plus Ri square divided by Ro square minus Ri square. So when we further go here, this will get cancelled, is equal to P into Ro square plus Ri square divided by Ro square minus Ri square. So this is the maximum value of tangential stress. Now the same thing that we will do for the minimum value of this stress. So I think I need to continue over here only. So sigma T is equal to sigma T minimum when x is equal to Ro. So how we will see this? Sigma T minimum is equal to here instead of x, now we will put Ro. Now be careful that we are using this equation, not this equation. So here P Ri square upon Ro square minus this is square Ri square into 1 plus Ro square upon Ro square. So the final equation will be equal to 2P Ri square divided by Ro square minus Ri square. So this is sigma T minimum. Okay, so what we will do is we will stop here. Let me add few slides so that we can copy this data over here. I think we will take this entire in one slide. Okay, so that's it. So what we will do now is we will continue further derivation in our next lecture. So that is the end of the second lecture. and we will continue this theory in our next lecture. Thank you for watching this video.